So tonight, I want to pick up where we left off on the Thursday review that's posted, so you guys can go back there and take a look at that. We covered a lot of stuff on confidence intervals and on single sample t-tests, the simplest version of the t-test. So now, in real life, we really wind up, more often than not, doing two sample t-tests rather than single sample t-tests. Single sample t-tests requires us to know the true mean of another population and to sample a population to compare to it. So in other words, we have to find the mean of our sample and compare it to a known value. So we only have a single sample that we're comparing to a known value. So I'll do a very quick example of that using SPSS when we get into the SPSS portion of this review. But usually, more often than not, we're working with multiple samples. In other words, we want to compare one group to another group. A group of people that were given an intervention such as training or a drug or some treatment versus a group of people that were not given that training or intervention. A group of people that were exposed to a material versus a group of people that were not exposed to a material. And of course, we're talking about numerical variables, blood pressure, blood sugar, so on and so forth. Okay, occasionally we're dealing with proportions as well, but most of the time it's numerical variables. Okay, so the first thing that I want to review is that when we're working with comparing the means of two populations, okay, using hypothesis testing, we're taking a sample from each of those two groups. Okay, so when I take a sample from two groups, I wind up with two means. I wind up with the X bar, the sample mean for the first group, and X bar, the sample mean for the second group. I also wind up with two standard deviations, a standard deviation for the first group and a standard deviation for the second group. Okay, unlike before, where I was only taking a single sample, I only had a single standard deviation to worry about. And then I would say to myself, gee, if I know the population standard deviation or the sample size is very large, well, I'm going to do a z-test. If I don't know the population standard deviation, which is usually the case because you're doing it from a sample, then in that case, I'm going to use the t-test instead. I'm going to use the t-value instead. Okay, but when we get into two samples, well, now we kind of double our problem, don't we? Have X bar 1, X bar 2, and we want to compare the two means, but the two standard deviations are different also. We get one from one sample, one from the other sample. Well, there's a couple of things that could be going on with those standard deviations. The first is, and this is from the document t-test variations, okay, there's three different ways that we might deal with with two populations, sampling two populations with the t-test. Okay, in the first one, we sample the two populations, we calculate X bar for one, X bar for the other, standard deviation for one, standard deviation for the other, and we find that the sample standard deviations are similar, they're close together. And we say to ourselves, well, maybe there's reason for me to assume that even though the means of the two groups may be different, the variability within the two groups are the same. So maybe I can pool those standard deviations and get a better idea of what the standard deviation is overall. Get a better approximation of the population standard deviation. So in general, this first set of formulas that you see here represent the calculations that we would use if we're going to assume that the standard deviations in the two groups are equal. Okay, so what do we mean? What's going to be equal enough? They're never going to be exactly the same. What's going to be equal enough? Well, for our purposes, if one standard deviation is less than double the other one, in other words, if they're close enough that one is not double what the other is, we're going to go with assuming that they're equal for our purposes. Okay, well, that leaves us with a quandary. Now, what do we do if one is more than double the other, if they're so far apart that one is more than double the other? Well, then we use these formulas for sample standard deviations that are not assumed to be equal because one is more than double the other. Okay, so formulas look intimidating, but they're really not that complicated. I'll go over them in a second. And then we also have the situation where we have two proportions. 10% of this population is diabetic. We take a sample of 100 people, 10 out of 100 are diabetic in this population. We take a second proportion, and 15 out of 100 people in that proportion, or 15%, are diabetic. So PCAP 1 is 15%, PCAP 2 is 10%, PCAP 2 is 15%. Now, how do we calculate that? And this is the formula that we would use for doing that. First, we'd calculate a pooled proportion for the two groups, and then we would solve this formula for the z-score for the two groups to determine how far apart they are and what the probability would be of us being wrong if we reject the null hypothesis. So this is the formula we would use for proportions, two proportions. So on these 3 pages, you have basically all of the situations where you would be dealing with two samples, whether proportions or numerical variables. Okay, so I'm going to go over some. Most of the time in real life, we'll be using SPSS to solve these problems. Okay, but so that we understand where these formulas are coming from, this is the way we would solve them. Okay, so let me get into first thing I want to do is perhaps go over. I'm going to open up the homework number 6B, and I want to go through that first, so we kind of have that down to start off with. Okay, so let me just get to that. See if this is readable enough for us to work with. Okay, so this is 6B, I believe. Yes. Okay. So I'm going to go through these questions so that we kind of get a basis of what we're working with here. Then I'm going to go back and I'm going to go through some other questions as well, maybe even some samples of problems that we might throw into an exam, and some exercises with SPSS. Okay, so let's take a look at this. The mean citywide score for the population of first-year high school students is 600. We know that mean. That's the mean for all of the 600 students. An investigator wishes to test if the SAT score for first-year psychology, we've seen this problem before, of course, is significantly different from the mean score of the population. The mean of a sample of 100 randomly selected first-year psych students is 624. So the mean for the population, mu, is known. That's 600. And we want to know whether these psych students, of which we only have a sample, right? A sample of size 100, a pretty big sample. Want to know if their mean is different. So first thing we have to do is set up a hypothesis test, our null and alternative hypothesis. Okay, so state your null and alternative hypothesis. First thing we know is we always talk about, not about the X bar, we talk about the means. So our null hypothesis is that there's always going to be that there's no difference, right? So mu, we have to see mu there, not X bar, right? So the mean of the population is equal to the mean for the psych students, or the mean of the population is not equal to the mean of the psych students. Mean of the populations is less than or equal to, or none of the above. Well, it's pretty clear there that this first one is going to be the choice that we want, right? Everybody comfortable with that? Our first null hypothesis is that the two means are equal to one another. Okay, I'm hoping that you guys are comfortable with that, right? Okay, now, next thing I want to do is I want to calculate how close. Well, before I go on with that, I didn't ask it, but do you guys see the alternative hypothesis here in this list also? What's our alternative hypothesis? Okay, anybody want to check say what our alternative hypothesis is? Well, our alternative hypothesis is that the two means are different, that they're not equal. Okay, actually, I'm seeing this got radio buttons on it. It should have little boxes, so you could check them. You could check them both, but I think either one it will be okay. So our alternative hypothesis would be that the two means are not equal to one another. Okay, so now once we've established that, now we have to compare whether these two are equal or not. Well, this is a single sample hypothesis test, right? So we have a single sample, X bar, right, is the mean is 624. Our standard deviation, our standard deviation for the sample is 100, right? Now we don't know the population standard deviation, so we typically would use the t-score. Now this is a large sample, so it's kind of a toss-up. You could probably use the z-score here as well. For the moment, I'm going to say let's use the t-score. Okay, so the first thing I want to do is I want to calculate how different that these are, whether these are different enough for me to reject the null hypothesis. And how do I know if they're different enough to reject the null hypothesis? Well, I need to determine what the t-score has to be that's critical, the critical t-score, which will give me 95% certainty that I wouldn't be wrong if I reject the null hypothesis. In other words, alpha is equal to 0.05. My acceptable level of error is equal to 0.05. So I have a t-table here, I'm sure. Let me go in here. Here's our t-table, and I'm going to look up to see what the critical value of t would have to be for that sample size. So here's my 95% confidence, right? So my 5% chance of being wrong is the same thing as being 95% confident. So I'm going to scroll down here to a sample size of 100. Actually, this is degrees of freedom, so it would be 100 minus 1 or 99, but that's very close to 100. And the t-score we would need to exceed in order to reject the null hypothesis is 1.984, right? I'm going to remember 1.98 for our purposes, right? So that's what our critical value of t is. So now I have to figure out what my t-score has to be, what my actual t-score is. How different are these values, right? So what is our t-score for a single sample t-test? What is that equal to? It's equal to t for 95%, or alpha is equal to 0.05. T is equal to x bar 1, our sample mean, minus, if we're a two-sample test, it would be x bar 2, but in this case, we know the second mean, right? We were told it, over the standard error, right? The standard error is another way of saying the standard error is the standard error is equal to the standard deviation of the population over the square root of the sample size. Again, we don't know what sigma is this time around. We only know what the standard deviation of the sample is over the square root of n. But that's a pretty good approximation, so we're going to use it. But that forces us to use the t-score instead. So the standard deviation is equal to, I think I said it was equal to 100 over the square root of the sample size, which is 100. So it's 100 over 10, which is 10. So our standard error is equal to 10. Okay, so now let's calculate our t-score. Our t-score is equal to x bar, which was 624, minus the mean of the population, which was 600. It's on the problem up a little bit higher, over the standard error, which is equal to 10. Okay, so what's it going to be equal to? It's going to be equal to 24 over 10, which is a t-score of 2.4. That could be negative or positive. It doesn't matter. It just matters that it's far enough away. It's enough t-scores apart, enough standard errors apart that we could say that they're different. Anybody remember what was t-critical again? What was the t-critical that we needed to exceed in order to reject the null hypothesis that the two means are equal? Anybody remember what that was? 1.98. Okay, I know it's late. I hope I'm not keeping you up, but I'm hoping that you guys are catching that. Okay. Okay, everybody agree with me on that? The t critical is 1.98. So my t score, these two numbers, 624 and 600, the x bar and the mu, should be wind up with a t score of 2.4. Can I reject my null hypothesis? I'll wait for somebody to give me an answer. Maybe it's not scrolling. Reject or fail to reject my null hypothesis. Right, right. Exactly. You do reject it. Exactly right. Because it's greater than 1.98. Excellent. Good. All right, good. Okay, so now that's as hard as single sample hypotheses get, right? That's really the what goes on with those. Okay, so now, okay, so we got in the process we answered question number 2, we answered question number 3, calculate the critical t-score, t-score we need. We did answer question number 4, and but we didn't calculate a t-value, okay, for this. Um, uh, we could, if we want to. I think I might leave that to SPSS since it's if it's okay for the homework, but I'll leave that to when we start talking about SPSS. Okay, based on the results you chose an appropriate conclusion, you reject the null hypothesis, accept the alternative hypothesis. Okay, let's take a look at this one. Study was conducted to determine if expected mother cigarette smoking has an effect on the bone mineral content of an otherwise healthy baby. A sample of 77 newborns whose mothers smoked have a mean bone mineral content of 0.099 grams per centimeter and a standard deviation of 0.026 grams per centimeter. Okay, we can start to ignore those numbers. So we got a sample size. We have a mean for sample X bar 1 for smokers, right? And a standard deviation for smokers. Well, now what about non-smokers? We have a sample size of 161 mothers who didn't smoke, and the X bar or the mean for that was 91, and the standard deviation was 0.025 or 25. Assume that the variance in the populations are equal. Well, you want to know something, we would have assumed that anyway, since one was not double what the others were. Okay, so let's state our null and alternative hypothesis. Okay, well, null hypothesis, the mean for the smokers is equal to the mean for the non-smokers, right? And obviously our hypothesis, alternative hypothesis, is going to be that they're not equal. Mean for the smokers is not equal to the mean for the non-smokers. Notice that we're talking about when we talk about our hypothesis, we're always talking about the population mean, even though all we know is the sample means. Okay, so go ahead, let's calculate the pools. Well, now we have to go back to our table, our description of how we're going to solve these things. Okay, in this case, we're dealing with a sample standard deviations that are assumed to be equal. So we're going to use this first page as our rule. Now, what we're really after is the t-score. So the t-score is the difference between the two means, just like before. Remember before it was x bar 1 minus mu? Well, this time we only know two means, x bar 1, two sample means, x bar 1 minus x bar 2. And then we're going to divide it by the standard error. Well, in this case, the standard error has to be calculated using a pooled standard deviation. This is our standard error. But before we can figure out what this is, we have to figure out what the pooled standard deviation is for this group. So the pooled standard deviation is going to be equal to the square root of sample size 1 minus 1 times the standard deviation squared for sample 1, and the same for sample 2, over the two samples sizes added together minus 2. So we calculate this number first and then use it down here to calculate our t-score. Okay, and the degrees of freedom are equal to n1 plus n2 minus 2. Okay, so let's go ahead and do that real quickly. Okay, see if we can get through this problem real quickly. And so let's see. Let me pull up a piece of paper here. Let's write down first what we know here from this problem. Okay, where'd the problem go? Let me get the problem back. Okay, good. Here's the problem. And let me pull back here to what the problem was. I can see what all these numbers were. Okay, good. I think I got it now. Okay, so let's see what I got here. It's going to be difficult for me to do this at the same time. I think if I squeeze this stuff together, I think I can squeeze everything in here. Okay, let's see how much of this I can get in here. Okay, so I got sample 1, right? So x bar 1, I got standard deviation for 1, right? And I got the sample size for 1. Okay, so sample size for 1 is 77. X bar for 1 is equal to 0.099. The standard deviation for the first group is 0.026, and this is for the smokers. Okay, well, how about non-smokers? Non-smokers. Okay, so that's x bar 2, or how about if I call this x bar s for smokers and x bar ns for non-smokers is equal to, for non-smokers, it's equal to 0.091, and the standard deviation for non-smokers is equal to 0.025, and the sample size for non-smokers is equal to, for non-smokers, is equal to 161. Okay, so let's figure out what our T critical is. That's the first thing I want to know. What does T critical have to be? How big a T do I have to have in order to reject that null hypothesis? Okay, so in order to do that, I need to know what my sample size is for degrees of freedom to calculate T critical. Well, as it turns out, in this particular instance, right, where we're doing a two-sample t-test with equal variances, well, it's equal to n1 plus n2 minus 2, which would be 77 and 161 minus 2, okay, which is going to be, let's see, it's going to be 8. It's going to be 8, 6, carry to 1, 13, 4, carry to 1. It's going to be 246, I think. Am I right? 77 would be 8, and 7 would be, nope, I'm wrong. It's 236. Am I right about that? Let's see. Yeah, 236. So the degrees of freedom is equal to 236. Well, I know without even going back to my t-table, I know that it's going to be even beyond what my t-table is, right? So you want to know something? Because the sample size is so big, I'm just going to go ahead and use 1.96, which is the same number I would have used for a z-score, simply because the sample size is so big. Had the sample size been small, had the combined sample size turned out to be, let me do that again, had the combined sample size turned out to be 16, 17, let's say, so 16 degrees of freedom, I would have used my critical value of T would have been 2.12. Okay, so in our case, it's going to be 1.96 because it's such a large sample size. Okay, so the next thing I have to do is calculate my standard error, right? Because I'm going to have to figure out how I'm going to do this math. Well, our standard error, remember that in order to calculate our standard error, first thing I had to do was calculate a pooled standard deviation. And how did I do that? Let's get our chart up here. Okay, here's that. Let me minimize that for a second. Okay, here's our formula for our pooled standard deviation. So our pooled standard deviation, right, is going to be equal to the square root of sample size 1 minus 1, which is 77, is 76 times the standard deviation for the smokers squared 0.026 squared. Okay, number's a little funny, but as long as you just keep doing what you need to do, it'll work out right. Times the sample size 2, which was 161. In other words, 160. That's a plus sign. Oh, I'm sorry, that's a plus sign in there. 160, make that a little clearer. 160 times the standard deviation for the second group squared. 0.025 squared over the sum of these 2 minus 1. That's our 236 again. We're going to take the square root of that whole thing. Okay, so now I like to use Excel to do this because I can do it in a few steps. I can always go back and correct myself and so on and so forth. So I'm going to pull up Excel for this. So you can use a calculator if you want, but I encourage you to use Excel for a lot of these things. Okay. Oops. I'm going to make things a little bit bigger so it's easier to see. Okay, so let me go ahead and do this calculation. I'm going to do it in a couple of steps. First thing I'm going to do is I'm going to do 76 times 0.026 times itself. 0.026 times 0.026. I could use the caret sign to represent the squaring, but it's just as easy to get multiplied by itself. Then I'm gonna do the second part of that numerator, right? It's equal to 160 times 0.025 times 0.025. Hit enter, and now I've got that number together. Let me just make sure I got that right once. Yep, that looks good to me. And now I need the sum of that, so I'm just going to add those two together. So that's the value that's in the top of my fraction. That I'm going to find the square root of. And 236 is in the bottom. So now, if I want to find out the square root of that divided by that, I can just say equals the square root of this numerator divided by the denominator. And it comes out to be 0.025. Okay, you guys okay with that? Notice that number is between my two 0.026 and 0.025. It's in between the two of them. And it's closer to this 0.025, isn't it? 253 rather than being closer to, it's closer here than it is there. That makes sense because it's a pooled standard deviation and this is a much larger group. Okay, so now that I've calculated my pooled standard deviation, which I'm going to write in there, it's equal to 0.0253. .0253. Okay, now that I've calculated that, now I can go ahead and calculate my t-score. And my t-score is equal to x bar 1, smokers, x bar for smokers minus x bar for non-smokers, over the standard error. Standard error is going to be equal to our pooled standard deviation, 0.0253, times the square root of 1 over, well, n is 77 for the first group, plus 1 over 161 for the second group. Right, so I'm going to have to calculate that before I actually, remember that's a plus sign in between. I'm going to have to calculate that as well. So again, I'm going to go back to Excel. Okay, let me bring it up here. Okay, so on the top, that's going to be equal to the difference between our two means, right? What were our two means? Our two means were 0.099 and 0.091. 0.099 minus 0.091. That's our numerator, right? That's our top. Now on our bottom, okay, I'm going to find out what the bottom is. Okay, let's see. It's going to be equal to, bottom's going to be equal to, well, first, I'm going to do this in a couple of steps. First, I have 0.0253. I'm going to just put that in there. Okay, and then I'm going to find out what that sum is equal to. Okay, well, I'm going to do that up here. So 1 over 77 is equal to this. 1 over 161 is equal to this. Whoops, got to put the equal sign in there. Is equal to that. So I find the sum of those two and find the square root. That's equal to the square root of the sum of those two. This plus this. Okay, and let's see what that comes out to be. Comes out to be 0.1385. Okay, so now this was our difference in our two means. And now I haven't found the bottom yet, have I? Now I have to multiply these two to get the bottom. Is equal to 0.0253. That's our that's that value right there, right? Times the value that we got for the sum of these two, which is equal to 0.13, and the sum and square root of those two, okay, which is equal to 0.053. So my numerator, whoops, let me just get that read. My numerator is 0.008, and my denominator is 0.003. So my z-score or my t-score could be either one in this case because the sample size is very large. I could just simply use z here, okay? And my z-score is equal to 0.008 divided by 0.0035, okay, which is equal to 2.28. Anybody remember what t critical was for this biggest sample? Okay, or in fact what z was, what t critical or what z was for alpha is equal to 0.05. They're the same because it's such a big sample, right? We're not going to differentiate. But yeah, it's equal to 1.96. Okay, so in this case, has my z-score or my t-score that I calculated, does it exceed t critical? The answer is yes. Of course, I can reject my null hypothesis and accept my alternative hypothesis. Now, I'm not going to ask you, I don't see myself on a test asking you to work out unequal standard deviations, or I don't even see myself, I may at some point ask you to work on proportions, but for a test, I'm not probably going to ask you to solve this particular problem. I might give you an SPSS output and ask you to work with it instead. Okay, so now let's take this now and let's look at some examples that you might actually see on an exam. Okay, so in addition to doing this kind of calculation, right? Remember we talked about on Thursday, we talked about, and previous sessions, we talked about confidence intervals for a proportion, confidence intervals for a mean, and so on and so forth, how to calculate them. Okay, but let's take a look at how we might get involved in some situations that involve these different kinds of samples that we might run into for SPSS. For instance, one of them, I'm going to open up SPSS. Okay, so I'm going to open up. Well, first, I'm going to take a quick look here. And one of these problems involved a single sample test. Here's a list of 10 people. There's measurements, 9 measurements. There's randomly sampled 9 people from this population. And these are the values that we got, whatever those values represented. But it's a single sample. And let's say I want to compare that to a known mean of some specific number. I can open that same sample in SPSS. Okay, I'm going to open in SPSS. Open, data. Okay, I'm going to go to, let me see here, where is it? Sunday, here we go. Here's our single sample test. Those same numbers are going to show up here. And in this case, I'm going to compare this sample to a known mean. Okay, I'll pick out, let's say, number 10. Let's say the mean of the population I'm comparing this to. Now, let's say the mean I'm comparing it to is 12, a known mean of 12, or a number 12. To analyze a single sample t-test, analyze, compare means. I'm going to move over here to one sample t-test. Okay, I'm going to move that sample into our test variable, and I'm going to tell it I want it to compare to the set value, the known other mean for the other population of 12. We're not going to get this here for anything but a single sample t-test, because that's a place for us to put the mean that's known. I'm going to click OK. It's going to go through the same calculation that we did before for calculating when we're calculating a t-score for a single sample t-test. So let's see what the t-test came out to be. It's 8 degrees of freedom, right? Because it's 9. It's a sample size was 9, so it's 8 degrees of freedom, and our t-score came out to be negative 2.158. Well, we know we would reject the null hypothesis if for this number of degrees of freedom that this t-score that we calculated exceeds t critical. Let's take a look at what t critical is for a sample of that size. Yep. Okay, what's t critical for 8 degrees of freedom? It's 2.3. Okay, so let's go back to our problem. Okay, does our t-score exceed our critical value of t? No, it doesn't. So in this case, in this single sample t-test where we compared the mean of the sample, which was 9.89, to a known mean of 12, x bar was 9.89, mu was 12, single sample t-test, we failed to reject the null hypothesis. Now, we have further evidence of it because in addition to giving us the t-score, it also gives us the p-value or significance of this test, which is in effect the probability that we would be wrong if we reject the null hypothesis. Now remember, in this case, we said alpha is equal to 5%, which means that our tolerance for being wrong is 5%. So we already said we can reject it because it doesn't exceed the t critical. But notice that our probability of being wrong if we reject the null hypothesis, in other words, this is how frequently we would expect this kind of outcome, at least 6%, at 6.3% of the time, even if this was from the same population, that big a difference, even if the sample was from the same population as the mean, right? So our chance of being wrong is 6.3% or 0.063, which is greater than 0.05. So we would reject the null hypothesis because our p-value or significance is bigger than 5%, and our t-score is less than our t critical. Both of those are reasons to reject our null hypothesis. Okay, so let's take a look at how we would deal with using SPSS, the type of example that we just discussed, where we would be working with a two-sample t-test. So here's a simple two-sample t-test right here. Let's look at the data. Okay, the data looks like this, males and females. Here we go, males and females. And we say to ourselves, okay, we want to compare the mean for this group to the mean for this group. And the only thing we don't know is, well, we got to calculate the means. We got to calculate standard deviations. The sample sizes happen to be the same. Sample size is 9 in both cases. Now we have to calculate our pooled standard deviation and our standard error and calculate our t-score just like we did before. Well, in fact, I have this same data set. As an SPSS file, which I'm going to open up now. If I can find SPSS again. There we go. Okay, so I'm going to say open data. And this time we're going to our 2-sample t-test. And I'm going to open it. And notice males and females are highlighted here. I'm going to say analyze. Compare means, well, this time it's not a 1-sample t-test. We sampled 2 groups, males and females. So it's a 2-sample t-test, or what we would call an independent samples t-test. So I'm going to click that. And I'm going to tell it, okay, these are the numbers in my samples. These are the way they were split up by gender, male and female. Those are my 2 groups. I do have to tell it what number represents those 2 groups. It happens to be 1 and 2. Okay, I'll show you. We can see that. If we went into the variable view, we can see that that's true. But I'll show you in a second. I'm going to click OK. Okay, and it does our t-test for us. Okay, just so you know, I'm going to go back to my 2-sample t-test. And I'm going to go to my variable view. And if you look under gender, the values that represent gender, 1 is female, 2 is male. You have to tell it, SPSS will ask you for what the representation is for those 2 things. Okay, so a little bit of a complication, but not too much of one. Okay, so I'm going to go back to our output. So here's our output. Well, this time, notice we got 2 lines for our calculation of our t-test. And in fact, we got 2 t-tests that were performed. As it happens, the t-values for both came out to be the same, 2.184, 2.184, right? Came out to be the same thing. Okay, so now I have to decide, well, which of these 2 tests do I use, the top line or the bottom line? Well, remember what our rule was for standard deviations. If one standard deviation is more than double the other standard deviations, we assume them to be unequal. If they're not double, then we assume that they're equal. Okay, that's as a general rule. Okay, well, 1.9, that's almost 2 times versus 2.7. Well, one's not double the other, right? One's about 35% more than the other, but it's not double the other. So I would assume equal variances, which is the top line result. Okay, now we have another way of determining that also, and that is this first portion of the t-test. Notice the t-test starts here. You see this skinny little line that's vertical here. It's kind of hard to see, right? Separates this part from the actual t-test itself. T-test for equality of means. It separates it out. So this part over here tests for whether or not the variances are equal. Okay, and the way it works is just like most other tests that we do statistically, we start out with the assumption that the variances are equal, and we only will go to the bottom line, variances not equal, which would usually happen if it's more than double, the differences. We only go to that bottom line if we get enough evidence from our test here to reject the null hypothesis that they're equal with less than 5% chance of being wrong. So here's our significance for that test, our chance of being wrong. So equal variances are assumed. Well, what would be the chance that I'd be wrong if I reject that null hypothesis? Well, it would be 24.5%, more than 5%, well more than 5%. So I don't reject that null hypothesis. I stick with the top line, just as I would have if I used my general rule of one's not double the other. So I'm going to stick with the top line. My t-score is 2.184, just like it was, pretty close to what it was before. Now, do I reject my null hypothesis? Well, I don't know if I reject it yet. I need to know what t-critical is. Well, when we do a 2-sample t-test, what number of degrees of freedom do we use? We add up N1 and N2, comes out to 18. We subtract 2, and that leaves degrees of freedom is 16. Now look, SPSS is doing all this for you, right? So we're just interpreting what SPSS has done. So degrees of freedom is equal to 16. So let's see what our critical value of t would be for 16 degrees of freedom. Well, it would be equal to 2.12 for an alpha of 5%. 2.12. And what did we calculate it to be? 2.18. So it's bigger than our critical value of t, which would tell us that we can reject the null hypothesis. Well, let me say, let's check our significance, our probability of being wrong if we reject the null hypothesis. We want that to be less than 5%. And in fact, just like this being bigger than our critical value, our significance or p-value is less than our tolerance for error. 0.044 is less than 0.05. So in both cases, tell me I can reject the null hypothesis. Okay, now what about if I have unequal variances? Well, it happens that I have an example of that. Okay, let's take a look at unequal variances. Okay, and here's another set of data. Again, very similar, males and females. We're comparing the average of this group to the average of this group. Our null hypothesis is that the means for females equals the mean for males, but we're actually going to compare X bar for females versus X bar for males, and we're going to look at our standard deviation and so on. So I'm going to analyze descriptive statistics. Again, two samples. It's independent samples. Compare means rather. It's independent samples because there's two samples. Okay, and I'm going to compare the two of them. I'm going to move values into there, gender into here. Again, I got to define the groups, 1 and 2. Click continue. I'll click OK. Okay, and it's done our t-test again. So if we were to use our general rule as to whether to assume equal variances or not, let's look at it this time. For males, the standard deviation is 1. For females, it's 2.793. So based on that, would you assume equal variances or would you assume unequal variances? I'm going to wait for somebody to tell me. Yeah, I agree. Unequal variances, right? Because one is more than double what the other is. Let's take a look down here and see if this test for equality of variances works out the same way. Now, again, we start with the assumption that the variances are equal, and we only reject that idea if the probability of being wrong is less than 5%. Well, in this case, the probability of being wrong, if we reject that hypothesis that the variances are equal, is only 1%. So I go ahead and reject that idea, and I use the bottom line instead this time. That's the main difference when I'm dealing with unequal variances. I use the bottom line instead of the top line. Notice that they're very similar anyway. So my t-score is equal to 2.511. Now notice something interesting here. The degrees of freedom, I don't know if you remember, but when we looked at that table, that description of these tests, okay, the description of the test for unequal variances, it was a pretty simple formula, a simpler formula than the other situation for calculating the t-value, right? This seemed a little easier than that pooled standard deviation and then having to do the second calculation. But calculation for degrees of freedom is quite complicated. A lot of times people would just say, well, just take the smaller sample and subtract 1 from it and use that instead of doing this big calculation. Well, SPSS ignores that. It actually does the calculation. That's why it winds up with such an odd number. That's why it winds up with such an odd number. For degrees of freedom, 10.152. Well, let's compare our t-value of 2.5 to 10 degrees of freedom. See, 10 degrees of freedom, the critical value would be 2.228. Well, that sounds like 2.511 would exceed our critical value of t, so we would reject our null hypothesis. Let's do our significance test. Our p-value of significance, the probability of us being wrong if we reject the null hypothesis, does it agree with that conclusion? Well, yes, it does, because there's only a 3% chance of being wrong if we reject the null hypothesis. So we reject the null hypothesis, and accept the alternative hypothesis that the means of these two groups are unequal. So I may ask you to do like a simple test like this, or I may just give you a table that you can interpret the table. You can use to interpret the table. But I don't think we'll be too demanding on this stuff. Okay, so there's one other possibility that we haven't discussed. And you might have noticed if I go to Analyze, Compare Means, there's a couple of other options here. This one we're going to get to in the coming weeks. This one over here is something that we started to discuss also, paired sample t-test. Well, what does that mean? Well, a paired sample t-test occurs when we give the same test, when we test a person, same person, before and after they've taken a drug or before and after an intervention, it's the same person. It's not two different groups of people, but the same person, the same measurement given twice to the same subject. Okay, so in other words, if I can pull up an example here, paired sample t-test, I'm going to look at it in Excel. So in this one, each person, this number two, this person over here, that person took a placebo for 2 weeks, and their blood level for whatever measurement we were taking was 6. Then they took the drug for 2 weeks, and there was no change. Well, this person took the placebo was 7, but the drug reduced it to 5. This person took the placebo. And by the way, even though they're in the columns of placebos first, drug second, the order that usually when they do a test like this, the order that they give them to the patients in, like drug first or placebo first, that's usually randomized as it would, but we're just organizing the data this way. 9, this person actually went up to 12, this person went down to 8. So now, really, we're not interested in comparing. It's not like this is one group of people and we're comparing it to a different group of people. This is the same person before and after. So what we're really interested in is the difference between these two. So that's equal to this minus this. And we could do that literally for each one of these values. So the idea here is that we're not interested in this measurement versus this measurement, but the difference for each person, whether their numbers went up or down and how much they went up or down. Okay, and we can add those all up together and we can actually take the average of them, the average difference for all of these 9 individuals. And it comes up to be a plus 1.5, went up 1.5 on the average for each individual. Well, let's think about this. If the drug and the placebo had no effect, we would expect to see no difference between the measurements for the placebo and measurements for the drug. So we would say that it came out to be 1.55, but what we would have expected is 0, that there's no difference between the two of these. In a sense, this is a paired sample test is really a single sample test of the differences versus the known value, the set value 0. So if I want to give this a try on this particular data with SPSS, I would go back to SPSS and I would say open data. Okay, and I would say, let's see, to sample, where is it? I got paired sample S. Okay, there we go. Okay, and in fact, I think this is the same data as we had there, right? And then this time I'm going to go to Analyze, Descriptive Statistics. Okay, I'm sorry, Compare Means, and I would go down to Paired Sample t-test. Now, paired sample t-test, it's going to ask me for 2 variables, the value for placebo and the value for the person when they took the drug. Same person took the drug. And I'm going to say, okay. And it's going to do that calculation for me. Now, notice only a single line here because this is really a single sample t-test. And notice it didn't ask me to compare it to anything because it knows to compare it to 0. So our null hypothesis is that there's no difference between that the difference between the differences between placebo and the drug group is 0, And the alternative hypothesis is that the difference is not equal to 0. In other words, it's different than 0. So let's see what our results were. So our mean was 1.556. We figured that out. That's our standard deviation. It calculates our standard error. So what is our t-score? Our t-score is 1.73. Right? So 1.73, that's pretty low, right? Especially for such a small sample size, only 8 degrees of freedom. We know that our t-value would have to be, I think it was something like 2.22 or 2.23 in order to reject our null hypothesis. So we failed to reject our null hypothesis based on that t-score. In other words, we can't reject the null hypothesis that the difference between the two groups is 0. In other words, there's no difference between the placebo group and the drug group. Okay, and in fact, if you look at the p-value, the probability of being wrong if we reject the null hypothesis is greater than 5%. So both of those agree. Our t-score is lower than the critical value of t, and our significance or p-value, probability of being wrong, is greater than 5% if we reject the null hypothesis. Okay, so I think that's basically what you might see. And in fact, you might be asked to actually, you're given the data set, SPSS data set, and asked to do this calculation in SPSS. That's pretty simple, right? Analyze the compare means and just wind up choosing the right test. Or I might give you a table and ask you to interpret it or decide whether the null hypothesis should be rejected or not. We might have some simple calculations on confidence intervals and a couple of multiple choice questions or something like that. But I'm hoping it won't be too difficult. Okay, so for those of you that are in the online group, you have the luxury of being able to do it online. On it's time limited, but you get to do it when you're ready. For you other guys, of course, like you're gonna have to gird your loins tomorrow and do your best at it, and then we'll figure out where we are from there. Okay, and we'll figure out once we figure out where we are, how well this has come across, then we'll see where we can go from there, and we'll also learn some very interesting tests going forward as well. Okay, so guys, I think I think that should help a bit, if you use that guide, for the types of tests that paper that shows those formulas, just as a reminder, even if you don't have to apply the formulas themselves, as a reminder. Depends on the class that you're in. Check Blackboard for the dates of the exams and the guys, you guys in the brick and mortar versions of this course or hybrid version of this course are doing it tomorrow. And you guys that are in the online group have it on a span of time. Yes, yeah, the online group. You're doing it next week. It'll have some more. You'll also have a bit more material on it because yours is probably going to include chi-square as well. So, but we have more. You guys have a little bit more time to work on it as well. So, the need for you guys is not as immediate. Okay. So yeah, I will have another review on Thursday, because we'll all be moving forward to chi-square by that time. So we're all going to want to learn a little bit about it. For the guys in the brick and mortar end, it's going to be more of a preview for them, I guess. And for you guys on the online group, you will already have had a taste on it, and it will be kind of another review for your exam. Chi-square is only on the exam for the online group. Okay, not for PH 750 or the 611. Okay, I don't think we did any chi-square yet in 611. Okay, but for you guys in 610, okay, we have an extra 2 weeks, really, almost, right? An extra week or two that we had to work on this because we don't miss sessions during the semester. So Like the brick and mortar guys, they missed a couple of classes. They missed a class or two because of holidays, especially Monday, attending on Monday. Okay, so good luck, guys. Don't be too nervous about this stuff. Just try and understand it. Try and get through it. It's not on the. It is on the exam for the online group, not on the exam for the brick and mortar people, for 611 or for. Well, you guys know we haven't covered it yet in those classes, I think. Right, Julian? What class? Which one are you in? Which class are you in? Oh, you're in online. Okay, so you've seen it. Where we've posted some material on it. And there's more coming this week on it. So we'll include that on there. I think. But probably won't be too intense, but we'll get a chance to go over it on Thursday. Okay, good. Which assignment is that? Was that 7? I think if you guys have a 7. Okay, yeah, that's not due until the 21st, I believe. Correct? Right. Oh, the multiple choice probably a little. Yeah, I guess there's probably more multiple choice. Probably more likely be related to the lectures than to the labs, right? The labs kind of are. Most of the stuff we do in the lab is kind of exercises, So I think most of the kind of background, the theory in the background, and it's simple things. Some things like, and also the textbook. Remember, we have a little bit of readings in the textbook as well. So what could be on the multiple choice? What could be multiple choice? Things like what assumptions? What are the assumptions that you make when you do uh, uh, a t-test? What is when you take a sample, right? What kind of are they random? Are they independent? And so on and so forth. Um, uh, uh, Maybe a question about the central limit theorem. What are some of the properties of the central limit theorem? In other words, does the does the population that the sample is drawn from have to be perfectly normal for you to apply the central limit theorem? Stuff like that. Okay, so I think that's more kind of the bailiwick of the lecture rather than the lab. But I'm sure that as we've gone through this in the labs, that a lot of this stuff, we've at least talked about in passing while we were working on the examples. Okay, so relax, go through it. Don't let this stuff make you crazy. Do your best on the exam, and once we get through the exam, we'll see where we stand, and we'll adjust accordingly. If we have to go back over some of this stuff, we'll do that. And uh, 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 if it turns out that we haven't done a very good job of really teaching this stuff, then we'll have to back up a little bit. We'll have to figure out some way to get everybody back on board with us. Take care, guys. Good night.